Okay, so I'm gonna finish or maybe not finish. I'm gonna keep watching the Professor Leonard 1.g video, and we'll see what happens, I guess.
Alright, so welcome back. We're talking about limits. We're going to start talking about piecewise limits. Now for us, we found out that when we're taking a limit, usually we can cancel out a problem, or if we can't, we use a sign analysis test because we have an asymptote. Hopefully you practice that in your homework. Were you okay with that idea? So generally what we're trying to do is plug in the number. Plug in where...
I think I did this on the Pause Online Math Notes thing. I think it's just you get like some restrictions or whatever for your function, and depending on what point you get, it could it could not be a limit, or it could be a limit. And yeah, I mean, I don't really, it's hard to explain, but I'm pretty sure I did this already.
X is approaching. If it works, great, that's your limit. If it doesn't work, well then you have to factor, do something to find that limit. Typically factoring we'll be able to simplify that a little bit, or we found out we can rationalize denominators and numerators if we have square roots. We can do things like that to work around that limit. Now what we're going to talk about today is some different aspects to that. We're going to talk about piecewise limits. I'll show you what you can do with those things. It's going to be kind of nice. You just got to follow me on this. Then we'll talk about trigonometric limits, and that'll end our day. We have a lot to talk about on trigonometric limits. So, piecewise limits. Here's basically the idea when you're talking about piecewise limits. A piecewise, of course, means different functions all mashed together that have different directions for each part of it. You all seen piecewise functions before. Piecewise limit says, what's the limit as we're approaching that interchange? Basically, does it exist? Does it not exist? What does it happen to be? So our idea is we're going to have to take some one-sided limits, because each piece is different, right? We're going to take one-sided limits and see if they match up. If they match up, great, limit exists. If they don't match up, then no, the limit doesn't exist. Are you with me on this? I'll give you a real nice way to do this, a graphic organizer. Hopefully this will help you out. And then, of course, if there's questions, man, ask. So let's talk about this. Our idea is we're going to find some one-sided limits, and we're going to see if they're equal. Let's start off with an example. Let's say that I give you this. I say that your function is actually made up of 3 parts. The first part says you're going to do 1 over x plus 2 if x is less than negative 2. I say you have a different range. You have x squared minus 5 if we're between negative 2 and positive 3. And lastly, our last little step, we're going to be the square root of x plus 13 if x is greater than 3. Now, because we have a piecewise limit, we basically have, in this case, 3 different functions. That means we can't just look at this thing, hammer at it, one function, and find out what is the limit of any particular place. What I'm going to ask you for is, can we find the limit at 2 and 3? As x approaches 2 and 3. Why 2 and 3? Well, if you look up here, that's the only place that could possibly have an issue, right? Is negative 2, that would have an issue. Everywhere else it's continuous, the limit's going to exist, no problem. Same thing here, that's continuous everywhere. The only problem would be maybe at the endpoints of negative 2 and 3. Here the only problem could be at 3 with that function. So we're going to talk about the limits as x approaches negative 2 and x approaches positive 3. Are you with me on that? So that's our idea here. What we're going to have to do is find our left side limit for each function and a right side limit, and see if they meet up somewhere, if they meet up at those points. Now here's the way that I like to do this. First thing I like to do is draw a representation of your graph, of your number line, basically. Just like that. break it up into the places where your piecewise function's broken up. What are those key points? What numbers delineates our function from the next piece of the function? Where does one function start and one function stop, basically? Negative 2, that's a key point, right? So we're going to have negative 2 on here somewhere. What's another key point for us? Let's call this one function 1 and function 2 and function 3. Can you tell me what function is in this range over here? What function takes over for this interval?
Function 3.
Function 3, because it says for any x's bigger than 3, I'm now function 3. Does that make sense to you? So I know that I'm looking at function 3 here. What interval, which function takes over in this interval?
Function 2.
Function 2, for sure. And that leaves this one with f1. Let's make sure. X is less than negative 2, function 1 takes over. Do you understand that this is how actually our graph should look? It should be function 1, then function 2, then function 3. And I'll draw this graph for you at the end, just so you see what this really does look like. You with me still so far, though? So here's the idea. If we want to find the limit as x approaches negative 2 and the limit as x approaches negative 3, we don't have to find one-side limits for all 3 functions, just the 2 functions that are approaching that number. So for instance, if I want to find the limit as x approaches negative 2, if I'm going from the left, which function am I going to use?
Function 1.
Function what?
1.
From the left, I'd be using function 1. Does that make sense to you? Now from the right, as we're approaching negative 2, which function am I using from the right?
Function 2.
Function 2. Yeah, that's right. So around this function, I'm going to have a one-side limit from the left using f of 1, the first function. Then I'm going to have a one-side limit from the right using the second function. Does that make sense to you? It's a way to picture this. How about around 3? We want x to approach 3. How about you guys over here?
Function
What
2 and
function
3.
are we going to use as we approach 3 from the left?
Function 2.
Function 2, that's right. That's in this interval. How about from the right? Function 3. We're not using function 1 over here, are we? We're not using function 3 over here. We're just looking around that number, what functions we have. So now, because we have this, it gives you a pretty good idea of what your graph looks like, right? This is how you make up your one-side limits now. Okay, so I'm going to take a limit as x approaches negative 2 from the left, a limit as x approaches negative 2 from the right, and I'm going to see if those two things are equal. If those are equal, then we'll have a limit as x approaches negative 2 in general. If not, well, then we won't. Do you all understand the idea so far? Are there any questions so far on the idea? Okay, so let's go ahead and let's try this. What's the specific function I'm going to use for this one? This is negative 2 from the left
So function
hand
1.
side. You all said that was function, which one?
1.
Function, well, what's function 1?
1 over x.
Now write that. This one, by the way, is going to be the hardest. For some reason. How about going from negative 2 from the right-hand side? What function would we be using?
Function 2.
Isn't this kind of nice? You just look at that, can't you? Kind of cool. Look at that one. Now, function 2, what's the actual function 2? So write that. So we said for this range from the left, function 1. This range from the right, function 2. We're going to see what these are. If they're the same thing, then our limit will exist. If they're not the same thing, will our limit exist?
No.
Okay, so we have that idea down. Now, how about we set the other ones as well? Let's start talking about the as we approach 3. So we're going to need, again, a limit as x approaches 3 from the left, 3 from the right. If they are the same, we'll have a limit at 3. Let's fill out the functions, though. Let's fill out the functions. As we approach, everybody, 3 from the left-hand side, which function are we using? And function 2, again, you said that was x squared minus 5, so we'll write that. How about from the right-hand side, what function are we using?
3.
Function 3. What's function 3? I'm assuming your mumbling was square root of x plus 13. Was that what you were mumbling? 13. Okay. Now here's the deal. I'm going to work this side, these ones first, then this one because that one's a little bit more difficult. Let me posit something to you. What I'm going to say is that if a limit exists, a one-sided limit definitely exists. Would you agree to that? If a limit overall exists, then a one-sided limit will certainly exist. Agreed? So a limit existing is stronger than a one-sided limit existing. Does that make sense to you? Well, here's the cool part about that then. And this, a lot of you were asking me, how do I find one-sided limits? Check it out. If you know for sure that a limit exists, then the one-sided limit will exist. Plug in 3. Ignore the from the left. Plug in 3.
4.
What do you get? You get 4. Guess what? That's your limit. Why? Because does the limit of 3, does the limit as x approaches 3 exist for that function? Absolutely, without equivocation, because that right there is a polynomial, right? And you know with polynomials, you can just plug in a number unless you have a problem.
True.
Well, if the limit at 3 exists, the limit from the left
side
certainly has
exist.
to. It must. That's a weaker statement.
Very true.
Plug in 3, you're going to get 4. Does that make sense?
Oops.
Let's try it next. Again, if a limit exists, a one-sided limit will also exist at the same number.
4.
So, ignore the
Yeah.
plus for a second. Can you plug
So it
in 3
exists
without a
as 4.
problem? What are you going to get? You're going to get 4. Saying the limit exists, therefore the limit from the right, well, it has to exist. If the limit exists, the right and left side limit for sure exist. They have to go to that same number. That's going to be 4. Now you're able to answer your question. Wasn't that nice and easy? You just plug them in. That's it. Just plug them in. If you can, just plug them in. Nice and easy.
And I guess on the left side, you're gonna have to do the sign analysis test.
Does this limit exist?
Maybe.
Why? Yeah. I don't care that they're not the same function. They go to the same value. Limit is 4. Raise your hand if you're okay with that one so far. Kind of nice, right? One-side limits aren't so bad. Piecewise functions, they can get kind of...
So this is gonna be an infinity answer, I think. This it's gonna be -1. So I'm gonna guess that this doesn't exist.
I'm asking you to find that over here, but not
Could be
too
wrong,
bad.
Maybe
Do you
there's
have
something
any
else
questions
exists.
on this? Because I'm going to erase it because I need the room. Any questions on that? Okay, so again, if a limit exists, a one-sided limit will exist. Find out your one-sided limits. If they're the same, then you limit at that point. For sure, you got it. Now let's start over here. Can I plug this into that function?
Yup.
Absolutely, that's a polynomial. So ignore
Good
the
one.
thing on the right. Plug in -2, how much are you going to get? -1. Absolutely, -1. Here's the issue, okay? Here's the issue. Ignore the from the left. Can I plug in -2?
No.
Aha. So what you're saying is that the limit at -2, you don't know whether that exists or not, right? You don't know. What's that mean? Can you cross out any part of this? Can you factor and cross it out? Okay, so think back. What do you use if you can't cross out a problem?
Sign
What do you
analysis
use?
Sign
The thing you couldn't abbreviate. That's right, the sign analysis thing. You have to use that. You can't abbreviate it. It's just going to look funny in your paper. But you have to use a sign analysis here. So if you have a sign analysis at -2, what we care about, what's happening here? What is happening at -2? Do you have a hole? Do you have an asymptote? Which one?
Asymptote.
Folks, you all should be able to tell them that. You all should know that at this point. If you cannot cross out your problem, what is it? It's an asymptote. So what do you have as you approach -2? It is certainly an asymptote, yes? We just want to know, is it going upwards or is it going downwards? What could you do to find that out? Any value to the left over here. So plug in negative
I would
3.
say it doesn't even matter. I mean, I know you have to find it here, but you just know that's infinity. And you know that -1 is definitely not infinity, so then you'd say it doesn't exist.
If you plug in negative 3 to this function, are you getting a positive or a negative? Definitely a negative. So am I going upwards or downwards? Like that, right? So here's what you're just finding out. What does this limit? I don't care from the right. Look, why don't I care about this? Why don't I care? Is this the same function on this side of that -2? Is that the same function?
So, oh, this doesn't exist. Or wait. Oh yeah, we don't care about the right. So it's negative infinity, so it does exist.
Over there? No, that's, we've already taken care of that one. I don't care about that. I just cared about this. So what does this limit equal? Can you tell me? Yeah, as we go towards -2 from the left-hand side, it is going like that. That's going towards where? Mhm. So let me recap just a little bit. What you're doing, you're breaking up your interval. You have 3 different functions in this case. You set up your limits around those breakoffs for your intervals. You'll use left-side limits, you use right-side limits, and you see if they're the same. Some of them are going to be easy, like what I showed you over here. Others of them, you might have to do a little bit of work. These ones you can just plug in. That one you can just plug in. This one, if you can't cross anything out and eliminate the problem, you've got to use a sign analysis test. Don't get stuck on that. Okay, you're going to have something like this on your test. Don't get stuck on, what do I do? Oh no, I can't plug in -2. What now? Sign analysis test. If you don't know what to do, you don't got to throw things. Jeez. My goodness.
Sign analysis test makes it angry.
It survives no crash.
You just got that? No, you just got that with some nice marks on it. Congratulations. Don't just get a new motorcycle, okay? Anyway, so this one, yes, you plug this in. This one, well, you can't cross anything out. You have to do a sign analysis test. Do what you know. Don't get stuck on it. If you can't cross anything out, sign analysis. That's only 2 things you got, okay? So we have this. We were able to plug in a number for the left of our interval. That's the side we were wanting. We went to negative infinity. Does the limit exist for this?
No.
This is -1. That's negative infinity. Last time I checked, those things aren't exactly the same. So this does not exist. But that, folks, is how you check. You don't check by plugging in numbers, okay, randomly. You check by showing your work like this. This is showing your work. Does that make sense to you? I don't want little tables or anything like that. See, look, the numbers are not the same. I don't care. I want you to show me what this is. Now, the way this graph looks, if you want to see why this doesn't exist, what this thing is a parabola, part of a parabola, that's symmetrical around the y-axis and intersects at -5. It's going from -2 non-inclusively to 3 inclusively. So if you plug in -2, what do we get? -1. Looks like that. And 3, if we plug in 3,
4.
what do we get out of that? 4? That's not really accurate, that part. Can't cross 3 and end at 3, but whatever. Then from there on out, we have the square root of x plus 13, which starts at 4 and takes off something like that. And then we have this one, which at this point, I'm sorry, this one. This 1 over x plus 2, if you graph that, that's some sort of descending function that goes like that, at that point. Does the limit exist as we approach -2? No. This is a rough sketch, by the way. Does the limit exist here? Absolutely, because that was closed off. By the way, it's a function because that's not equal to and that is. That's okay. We don't fail that part. This part would have had the open circle around it, but it's filled in by that point. So we have this parabola. Limit exists there? Absolutely. Limit exists here? No. Negative infinity and a value. Raise your hand if you're able to follow that and feel okay with it. Good deal. Are you ready for some trigonometry? I know it's supposed to be Trigonometry Tuesday, but we're a day early, so it's all good.
Was that one of your drinking party ideas?
Drinking party? I don't have drinking parties. Kool-Aid. Limits of trig functions. Okay, there's a couple things you have to buy in on for me to do this properly. And the first thing you got to buy in on is that sine and cosine are continuous everywhere. Continuous means you can draw it without lifting your pencil off the paper.
Mhm.
Can you draw sine and cosine such that they are continuous? Do you ever lift your
Yeah,
pencil
not
off the paper?
doing
No, so they are continuous. So first thing, this is going to come up later in our class, but I want to say it now. Sine and cosine are continuous everywhere. True enough. True enough. So, because we can do that, because there are no problems, we can use something that we use for polynomials. You see, polynomials were continuous everywhere. If you think about any polynomial, I'm not talking about a rational function, okay? I'm not talking about denominators.
So you're always gonna be able to plug in.
I'm not talking about roots that we have over here. This is a rational function. Clearly, it's not continuous everywhere. -2 fails. This is not continuous everywhere because it doesn't even exist for part of it, okay? So we're not talking about that. What we're talking about is continuous functions like this one. That's continuous everywhere. You're not gonna have a problem, no holes, no asymptotes. Agreed? Sine and cosine, we just said are the same thing. Therefore, if we have sine and cosine are continuous everywhere, we can apply the same logic and say, then the limit of sine of x as x approaches a is, what do you think?
A. I think.
It's not a.
Oh,
It's not
okay, never mind.
a.
One. Because if you draw it out, say this is A. Well, no. It could be between 1 and -1, right?
You wouldn't say this. You wouldn't say the limit as x approaches 5 of x squared minus 5 is 5. That's not true. What would you do to find it?
Plug in
You would plug it in. So to find the limit of this, what would we do? We plugged in, right? It wasn't -2, it's what we got after we plugged it in. So it's not a, what is it?
Sine of A.
Sine of a, absolutely.
Oh. Oh, okay. Well, yeah. I guess.
Likewise, because cosine is also continuous everywhere, we can do the same thing. Oops. Yeah, that's true. It says that nothing bad happens, basically. Right? That would be something bad happening. Hang on. There we go. That looks a little bit better. What about tangent?
It's not continuous.
What about tangent? So my question is tangent continuous everywhere?
No.
Draw a tangent with your hands. How's it go? Looks like you're dancing. Go. Yeah, you're doing that. I should have used that. I went out dancing the other night. I should have used my S curves. Would have been the hit of the party. Probably not. Maybe. Probably not. Okay, so we got to do a little bit more work. Since it's not continuous everywhere, we're going to have to break this down a little bit. So the limit of tan x as x approaches a. Let's figure this out. Tell me what is tangent. Use an identity. What's tangent? Sure. So we know for a fact that the limit of tangent is the same thing as the limit of sine over cosine.
True.
True? Very true. Very true. Now, there was one property of limits that said you can separate limits by division. Remember that property? Kind of cool. Let's do it.
Oh, true. So then you don't gotta deal with all that. Just like the, just like how you can separate everything into a polynomial.
Okay, okay. So limit of sine, limit of cosine. Do we now know what the, ignore the bottom. Do we know what the limit of sine x is as x approaches a? Sine a, sure. So this says, okay, I've got sine a. What's the limit of cosine as x approaches a?
Cosine.
What's sine over cosine? Aha, and you go, yay! What's the one thing I've screwed up on?
Cosine can't be
Say that again.
0. Cosine can't be 0.
Why can't cosine be 0?
Undefined.
That was the one thing, that one little condition about that property. If you remember, it said you can do that provided that your denominator, when you split that up, doesn't ever equal 0. And so we'd say, sure, the limit of tan x as x approaches a is tan a, except at certain points. At certain points, and that's where cosine would equal 0. That specifically is the reason why you get all those asymptotes on your tangent line, is because tangent is sine over cosine. So naturally, if it's sine over cosine and cosine equals 0, you have an asymptote. Remember the asymptote idea? You can't cross it out, you get an asymptote, right? It works all the time. So that's why we get those asymptotes going on. And those asymptotes occur at x cannot equal, or we will have a discontinuity, because right here, you go, oh, let me cross some purple so you see it a little different.
So basically you can plug in, you can plug in a, unless it's 0.
Cosine x cannot equal 0. If it does, you have a problem. Where that happens is every plus and minus pi over 2. So pi over 2, 3 pi over 2, things like that.
Cosine x or cosine?
Either one. Cosine x can't equal 0. At those points, you could say x can't equal these things. So, or cosine a. It really doesn't matter. Say cosine a. That makes a little bit more sense. Cosine a can't equal 0. If it does, you get a problem. So tangent wouldn't even be continuous at these points. Plus or minus pi over 2, because when you put those into cosine, you get 0. Plus or minus 3 pi over 2, and so on. And you can see this in the domain of tangent. If you look at the domain of tangent, that's why you get those asymptotes. Every pi over 2, remember tangent? Pi over 2, asymptote. 3 pi over 2, asymptote. And so on and so on and so on. And negatively as well. You guys all right with this so far? This is our basics. You guys okay with our basics? Start ramping it up a little bit. You're like, no, this is fine. Let's just stick with this. We're good.
We need to practice this a lot more.
Too bad.
So do you expect it to Steve? Okay. So we disappointed a lot this time.
There you go. That looks messy enough, doesn't it? How about that?
Yeah.
Sweet.
Do this.
Oh, okay. What in the world? Let's just give up. Call it a day. You ready?
Yes.
No. Let's do this stuff. Math. We just watch football. Can't do math and football. They're oxymorons. Mathematical football. Really an oxymoron. Yep. Brain injuries and football, that goes together. Not math and football. It'll work. Okay. What can you do with this? Well, I'll tell you something. You can, this is interesting, but if a function is continuous, you can treat it like a composition. Is cosine continuous everywhere? So what you can do with this is kind of cool. What you can do is say, all right, since cosine is continuous everywhere,
Wait, you can't do
you can
this.
do a
It's like
composition.
this.
Cosine is continuous. So, by composition, it's actually reverse composition. Look what you can do. You can say, instead of taking a limit of cosine of something, you can actually do this. It's very much like removing an exponent from your limit. You can say, I don't want to deal with that. I want to deal with cosine of my limit. That's legal. Why would you rather deal with that? Have you seen things like this before? Actually, I think I've given you that exact same example so far in this class. You've seen things like that. Can you do this limit? So as long as you can do this limit and don't forget about your cosine, you'll be fine.
Yeah.
It's interesting to think that the angle now is a limit. That's weird, right?
Okay, so you can just do that, really? Yeah. Something like that.
So cosine of, what are you going to do with that limit? What are you going to do? First, you're going to try
Factor,
to
simplify.
Before you factor, you're going to try to
Plug it in.
Try to plug it in. I mean, may as well just try that. If you plug in 1, though, you're going to get 0 over 0. What does 0 over 0 tell you? Is factoring going to work or not?
Yes.
Yes, 0 over 0 tells you that. So you're going to factor it. Probably going to work. Now, we've seen one case where it doesn't, where it was a double root. Okay, that happens. But factoring is something you should try first. So we'll have the limit. X goes to 1 of, well, I know y'all can factor. We got x plus 1. We got x minus 1. What can you do now? Sure. What was that discontinuity that we just talked about? Was that a whole or an asymptote in this particular case?
Whole.
Whole. Whole. Sure, because you can cross it out and there's no more problem left. That was a whole. Now, other question, let's see. Oh, I had one more, it's on my mind. Ah, forgot it. Cross it out. Do you have any problems left? Notice how we have to keep writing limit until we actually evaluate the limit. That's an important part of it. What can you do? Can you plug in the number and be okay?
Yes, sir.
So then what we have right here is cosine of, I know I can just plug in 1. 1 plus 1. What's cosine of 1 plus 1?
2.
Cosine of 2. Done. Cosine of 2.
We can't do that.
We can do 1 plus 1. I like 1 plus 1. How do you feel okay with this one? So we can treat that like a composition.
Why couldn't we just insert the one that, with the initial problem? Why do we have to pull the cosine out? Can you just keep writing it the same way and come to the exact same answer?
Yeah.
Would that be still an acceptable way of writing it?
I don't know. Just showing you can do it. Because a lot of people go, what do I do with that? And you go, well, can you still factor it? Can you still cross stuff out? And the answer is, well, technically no, because it's inside of cosine. But as soon as I move the cosine outside, see what we're dealing with now is a limit, and now it's not a domain problem because we're not actually approaching the 1. So yeah, then you can. Does that make sense?
Okay, so moving the cosine out is just a matter of semantics, basically.
Yes, yes, but important semantics, nonetheless. So can you do it? Yes, you can do it. Does that answer your question? All right. Would you like to try one more?
I don't get it though, because you can't do cursive 2. It's like if I plug in cursive 2. Oh wait, 2 radians. Okay, never mind. What is that? That has to be between 1 and -1. You're not gonna get a value that's less than -1 or greater than 1. Like when you plug it in, but you can plug in 2 radians, so cool. My bad. I think that's how you write it.
Answer is
Yes.
most of the time, yeah. Unless I'm really tired.
Is it ever changing on the left one? One could always wish.
I don't even drink coffee. Oh man, if I drink coffee, you guys would be in trouble. If I drink coffee that day, it's like crazy. Yeah, so basically, do you actually have to pull out the cosine? Yeah, you can. You can. That's the reason why this is allowed to do it. Do you have to show me that? I don't really care. What it basically says is if you can plug in the number, you can do it. That's what cosine being continuous everywhere says to do. Also says that you can still cross stuff out as you're going through your problem. Because it's a composition, it's continuous everywhere, you can pull that out. Does that make sense to you? So can we try to plug in a number here? Is that okay? Sure, as long as we don't run into an issue, i.e. you plug in something that's not even in the domain, like a negative root, or you have a denominator that's 0. That would be the only issues you have. Do you have an issue if you plug in pi over 2 here?
No.
No, actually, if you look at this, that's a polynomial, right? Plus a function that's continuous everywhere. That means you could split that up by addition. We knew limit rules for that. You could do this one by itself, just plug in pi over 2. You can plug in pi over 2 to the cosine because it's continuous everywhere, not a problem. So that says that, just like other limits that we're dealing with, try plugging in the problem first. If you can, no problem. So that would be 3 pi over 2 squared plus cosine pi over 2. What's all this going to give you? Not as a decimal. Oh, come on. What's pi over 2 squared? You can say pi squared. It's okay. Pi squared over 4. Very good. So this is going to give you 3 pi squared over 4. Are you following me on that? Okay. What's that going to give you? Don't say it out loud. I want you all to think about it. You need to know that. I said don't say it out loud.
Oh. Yeah, this does give 0.
And let's hold it in. equals 0. Notice how at this point I don't have to write limit anymore. I actually inserted the pi over 2. You guys see that? That's your answer.
So once you're no longer dealing with variables, you don't have to keep writing limits.
As soon as you evaluate your limit, at that point, no more limits.
So what if you keep doing step after step? You know, because when I write it out, I do this part of the math and this part of the math, and I keep continuing on. But once there's no longer variables, then
Once you evaluate the limit, no more limits. Once you are able to plug in that number, no more limits. Because you've done the limit, right?
yeah, I just kept going on my homework. I kept writing it over and over and over again.
Well, you should. You need to write it. I had to write it here. I had to write it here, here, but not here, because I was able to plug in the one.
Now, what if we maybe say we write it too much? Are we
Like
going to
here?
be knocked on it? Yes.
There is no more limit here.
So if we wrote limit in
Yes.
there,
The whole thing is you got to know what a limit actually is, right? You got to know that a limit is what does the function do as you're getting to that number. You got to know that as you're getting to that number, if it's a polynomial considered everywhere, you can actually plug it in, and that is your limit. Okay, you say, this is still a limit of something. No, it's not. That is the answer to your limit question. But it's, that was a good question, though. I'm glad you brought that up, because maybe other people were confused about that. It's a good question. Remember something a little bit more interesting? You know what interesting means in mathematics, right?
harder, scarier.
It's scary. Yeah, it's a little bit scary. I'm going to show you something. It's kind of cool. It is not my Darth Vader mask. It was pretty cool. No, I'm lying. My parents once told me that I had a stormtrooper mask, but I've never been able to find it, so I know they're lying. They're like, oh yeah, we bought that for you. It's like when you're like growing up and you ask your parents, have I ever been to Disneyland? Like, yeah. But really, it was just a park down the street with some guy named Greg. Same thing. That's Mickey Mouse. No, that's Uncle Greg. Okay. Okay. Let's try that. Let's try that.
Bruh. So. Bruh. Can you just take sign out like you did in the one? So it's like you say sign is continuous, so by composition take that out. X over X, 0. I don't know, man.
Oh, okay. let's go through the process of finding a limit, all right? The first thing you try to do is what?
Plug it in.
Okay, you try to plug it in. So you plug it in, what's sine of 0?
1.
No, sine of 0 is not 1.
Mm-hmm.
Sine of 0.
What up? Unit circle. Isn't it 0?
0 is 0.
0.
Over how much?
0.
Can you factor sine? Have you ever been able to factor sine in your life?
No.
No. No. So can you factor out anything and cross anything out? Can I just cross out the x and x and get sin?
No.
Yay! No, that doesn't work, okay? Sine has to have something next to it. If you do that, you have sinned in mathematics. That's not acceptable. That you can't do that, so we're basically stuck. There's no way to do this unless you want to just plug in endless numbers. There's no really a way to do this, but we're going to find a way to do it. You ready to find a way to do it? We use some trigonometry. Here's our idea.
Are we
Let's see if I remember
manipulating
using
the
it in a
trig
while.
identities and all that?
First thing we're going to do, oh yeah, we're going to bound this. We're going to make up a triangle. So, what I'm going to do is take part of my kind of a unit circle, not really, make it better. That's better. I'm going to take my unit circle. What I'm going to do is take an arbitrary angle. I can't be specific because, of course, we want this to work all the time. So I'm going to draw that. Now, what I'm going to do from this, I'm going to make up two triangles. I'm going to drop a perpendicular right from here. I'm also going to drop a perpendicular.
Why though?
It goes like that.
For what?
Okay, so let me define a couple things. Firstly, we're going to call x our angle.
This is a small piece of paper this time.
Second thing, what do I need? I need this.
Usually you got a big one.
I need that. Now, what I'm going to tell you is if we need to solve for that, let's see. This is going to be our tan x. How far is this distance right here? From here to here?
Yeah, 1.
Why?
Unit circle.
So, would you agree that, stick with me here, folks. Are you okay that x is our angle, firstly? I'm
Sure.
calling this length y. Okie dokie? And this is 1 from here to here. That's 1. Give me the relationship of tan x then.
Okay. Y over 1, y. That's y. Still don't see where he's getting at, but
Sine over cosine, yes. In the specific instance with a large triangle. Tangent is opposite over adjacent, true? What's the opposite? y over 1. 1, because that is the unit circle. Well, interestingly then, y equals tan x. So this equals tan x.
Okay. What's this point though?
Oh, let's see, one more thing. We also need this distance, and we need that distance right there. So let's say, what do we want to do? This coordinate is, what's the coordinate on a unit circle?
Square root of 2/2.
Well, that would be for a specific angle. What is it sine,
Sine.
cosine, or cosine, sine?
Sine cosine.
Wait, what? Oh, it's cosine.
Geez, I'm asking you, come on, you gotta know this.
Cosine, sine.
Agree? Okay. Because yes, sine x is typically y for an inside triangle. What that means is, I'll try not to screw this up too much for the inside stuff. That means that our x for this inside triangle is cosine x. Do you agree? That means that our y is actually sine x. Right? Now, also, what we're going to be doing is looking at this not this. That means that our y is actually sine x. Right? Now, also, what we're going to be doing is looking at this not this. Well, this one gives our height, but also this one. That triangle right there.
Bro, what is dude
What we're
doing
going to
actually?
be doing is comparing the areas of these triangles. So let me recap just in 30 seconds what we've done. We've gone ahead, we made up three triangles. This one just gave us the height. That gave us the height. This would be cosine, but more importantly, this height is sine x. Do you all agree with that one? Furthermore, if I call this y is equal to tan x because of the relationship of x and 1. You guys okay with that one?
Wait, what?
Y is equal to tan x because of the Furthermore, if I call this y is equal to tan x because of the relationship of x and 1. You guys okay with that one? Okay.
Yes.
Now we're ready to compare the triangles. So we've actually got three things going on. I need you to see all three things. First, we have a big triangle. You see the big triangle, yes?
Mm-hmm.
We have a smaller triangle, that's this one. So we have big triangle, we
Big
have
triangle,
small triangle,
small triangle.
and then we have sector. Do you agree with that?
What?
So what
Sector.
we want to do is consider the areas.
What is even going on?
We have big triangle, we have
Big
sector, and we have small triangle.
Alright, big triangle, sector, small.
Can you tell me how you find the area of a triangle? It's the area of a triangle.
Half times base times height.
Or base times height over 2, yes? 1/2 base
Same
times.
thing.
Let's look at the big triangle. What's the base? Base is 1. Very good. Times. What's the height? Instead of y, let's say tan x.
Okay. So tan x over 2.
And to find the triangle, I divide by 2. I need to show a hand seeing if you're okay with the area of the large triangle. Base times height over 2, we have base 1. Height is y, yes, but y equals tan x. I'm going to use tan x because I want everything in the same variable and all in x's. And then divided by 2. Let's do this small triangle, then we'll talk about the sector. Small triangle, that's this one right here. Not this too small one, but this one right
Okay.
there. Are you with me on that one?
Yes,
It's-
sir. So it's got a base of 1,
That
height
one.
of sine x.
And that's the big one.
Sine x over
Okay.
2.
And then we'll talk about the sector in a moment. What's the base of my smaller triangle? What's the height? The height of my smaller triangle? Sine x, not cosine x, right? Cosine x would be the, sine x would be the height of the smaller triangle because that is actually a point on the unit circle. Do you believe me? So that
Yep.
would be sine x. And then, well, Oh, shoot, sorry. I'm off one. 1 times sine x
Oh.
over 2. Are you okay with big triangle and small triangle?
What
You
is
are
the
with that
sector,
one.
dude?
Do you know how to find the area of the sector?
I don't even know what the sector is.
Area of the sector.
No, what are we talking about?
Which one of these are we talking about?
This is the sector.
Oh, okay. That thing.
Hi, slice.
No. No idea, man.
The area of the sector minus the small triangle.
Sure. How do you find the area of a sector?
No idea.
Use a big triangle.
There's actually a formula for it. It's this. It is your radius times your angle over 2.
Radius is 1 times your angle times the angle over 2. Really? Okay.
Radius angle 2.
Bruh.
You ready for the math magic?
Somebody hit the camera.
Ready? But you have to find one thing. You have to agree that the area of the sector is in between the areas of the big triangle and the small triangle. Would you agree with that? So it goes big triangle, then sector, then small triangle.
Yep.
True. So what we're saying here is that the area of the small triangle is less than
The sector.
the area of the sector
It's less than the big one. 1 tan x over 2.
which is less than the area of the big triangle.
Sure.
Agreed or not? What can I do to the 2's?
Get rid of them.
If I multiply all
No.
those inequalities by 2, which is legal, what
Yes.
happens to the 2's?
Yes.
2's are gone. 2's are gone. So what I'm going to do is change this into sine x is less than x is less than tan x. Some basic algebra. Basic algebra. You okay with that so far? Now here's the cool part. What I'm going to do, I'm going to divide each of these 3 things by sine x. Where sine x is positive, it's in the positive quadrant. That's okay. We're talking about a positive angle right here. What that means is that we're not going to change around these inequalities. So then this does that. You still okay with that so far? We divided everything by sine x. How much is tan x over sine x?
1 over cosine.
Sine
Square.
Say it again.
1 over cosine.
1 over cosine, because tan x is sine over cosine, yes? Divided by sine, that means you flip, multiply. You're going to be getting rid of over cosine, yes?
Sine over cosine. One over cos x, because, okay, wait. Sine, I'll write this in red. Sine over cosine over sine over 1. You got sine x over sine x cos x. Sines cancel out 1 over cos x. Yeah.
Divided by sine, that means you flip, multiply. You're going to be getting rid of those signs. So you're going to get 1 over cosine. We're almost done. Cosine. We're almost done. here's what I'm going to do. I'm going to reciprocate each of those fractions. I'm going to reciprocate the 1, this x over sine x, and the 1 over cosine x. What that's going to do is also flip around my inequalities. If you reciprocate that, it's going to flip your inequalities. Does that make sense to you? That's a mathematical truth. So I'm going to have 1 still, because the reciprocal of 1 is 1, is greater than sine x over x, which is greater than cosine x over 1. Do you see this thing anywhere? Do you see it right in the middle? Do you see how it's squeezed between two functions? It's squeezed between 1 and cosine x. Does that make sense? Now here's the theorem. It's called the squeeze theorem. The squeeze theorem says if the limit of this goes to something and the limit of this goes to something, then the thing in the middle has to go to that same limit if these are equal. Does that make sense to you? It
Okay,
says
that
I'm
makes
trying to
sense.
take a limit as we go to 0. Agreed? So then the limit of 1. What's the limit of the number?
That would have to be 1, right? It's a constant.
1. As x approaches 0, can you tell me that? What's the limit of 1? Doesn't matter what we're going to, right? The limit's 1. Tell me, what's the limit cosine x as x approaches 0?
Um. One. Oh, okay. So sine x over x has to be 1. Because of the squeeze theorem or whatever. Whatever you called it. Wait, was it as x approaches 0? Yeah. Okay. That's why you put them here. I equals 1.
Now, what do you get of cosine of 0? What's cosine of 0? Cosine of 0 is... It's not 0.
1.
It is 1. Here's what that says. Check it out. This is by the squeeze theorem.
Squeeze theorem.
It says that right now, if I take the limit sine x over x as x approaches 0, it was squeezed between two functions whose limit was 1 as we went to 0. It says the limit of 1 is 1. It says the limit of cosine as we approach 0 is also 1. What does this limit absolutely have to be? If it's between those two functions, the limit has to be between those two functions, only they're going to the same number. What's that limit? It has to be 1. It's squeezed. It's saying the right bound is 1, the left bound is 1. Can it be anything different than 1? No, it has to be 1. Technically, I'm supposed to have these throughout the whole thing. Throughout the whole thing. It has to be 1. Technically, I'm supposed to have these throughout the whole thing. And that's the big punchline for this part right now.
We're not done with these, are we?
No.
Can't get it.
This part right now.
We're not done with these, are we?
No.
No. No. Okay. That was a big proof. That's what it was, right? A proof. So, let's see. Yeah, I mean, I get the thought process, right? But it's a lot, so.
So again, what we just did, we learned one thing about this. We learned last time that the limit as x approaches 0 of sine x over x was equal to, what was it equal to, do you remember? 1. Okay, and again, for the last time, we did not prove the squeeze theorem, we used the squeeze theorem to prove this thing.
Seriously? So you just gotta do that every time then?
We bound it between two functions whose limit was 1. Therefore, this was in the middle of it. That limit had to be 1 as we approach 0. So this equals 1. That's number one thing you gotta remember. You gotta remember that one, that's gonna be in your head, right? So memorize that thing. When x approaches 0 of this function, you get 1. If x approaches anything else besides 0, well, it doesn't matter. You can just plug that number in. Okay, that's fine. Now, there's a couple of them that we might also want to know. Is there a relationship for cosine, firstly, and is there a relationship for tangent? We're going to look at those today. Then I'll show you how to put everything together and do any limit, well, that's reasonable, of some trigonometric functions. You ready for it?
Yes.
It's no Monday excuses this time. It's not Monday. It's Monday. Monday. No, it's Tuesday. I got you, Tuesday. And Wednesday. Friday. It's Friday. Okay, I can understand that, but no. It's Tuesday today. We're rolling. So, number one thing. Number one thing. Can we find the limit as x approaches 0 of this? One minus cosine x over x. Well, let me ask you the question. Can you just plug in the 0? If you do plug in the 0, what do you get?
Undefined.
You get 0, 0. What's cosine of 0, folks?
1.
You didn't know that. Cosine
Oh,
of 0
oh.
is 1. So on the numerator, you get 1 minus 1. That would be 0, right? And of course, if you plug in 0, x.
Wait a minute, 1 minus cos x is sin x. Isn't it?
0, you get 0 over 0. That's a problem. Can you factor 1 minus cosine x and cross out
Yeah,
the x on the
sin x.
bottom?
Well, it's
There's
you
nothing
can't
we can do
factor
with
it.
that. We're going to have to find some way around it,
Sin
just
x.
like we did with this one. Are you ready for it? It's not going to be nearly as time-consuming or mentally consuming as this one was. Okay, this one's actually quite basic. Here's what I'm going to do. What I'm going to do is find some way to see some sort of an identity in here. So what we're going to try to do is work around this 1 minus cosine x. And one thing I can do, perhaps multiplying by the conjugate would help us. Remember what the conjugate is? Just changes, what about that? Yeah.
Okay. One plus cos x minus cos x minus cos. Oh wait, it has to be squared. Okay, I forgot. So that's how he's gonna get it. So it's gonna be 1 minus cos squared x, I think. Yeah, 1 minus cos squared x over x 1 plus cos x. This is sin x plus cos squared x. And we'll see what he does.
That's it. So in our case, the conjugate would be 1 plus cosine x over 1 plus cosine x. Okay. Well, let's keep this going. Then I've got a limit as x approaches 0. The denominator is now x times 1 plus cosine x. You guys okay on the denominator? I haven't distributed anything, I'm just putting those together for right now. Now, could you tell me on the numerator, let's do a little work here. What am I going to get if I multiply 1 minus cosine x times 1 plus cosine x? What would you get out of that? Okay, try it on your own. If you can't do it in your head, try it on your own. Distribute it. Foil it out. You know you've got this, right? You know you've done that. The first thing you should be getting is a 1, yes? Then you're going to get plus cosine x, and you're going to get minus cosine x. Do you see that? What's going to happen to those middle terms? They're gone, so we're going to have 1. And then lastly, you're going to do cosine x, cosine x. Is that going to be a plus or a minus? Minus what? Cosine, not just cosine x, cosine. Yes. Oh, now here's the deal. Using your massive knowledge of trig identities, some of you have and some of you don't have right now, to be the brutally honest truth, what is 1 minus cosine squared x equivalent to?
Wait, did I say
using
sine
Pythagorean identities? Oh, you do have that knowledge. That's awesome. Very good if you know that. That's right. Because, listen, if sine squared plus cosine squared equals 1.
Oh, wait. Sine squared x over cos squared x times 1 over x. This is tan squared x over x, right?
If that's true, which it is true, and if I try to make this out of this thing, that would be subtracting cosine, right, from both sides. If I do that, we make up another identity. We make up the identity 1 minus cosine squared x is equivalent to sine squared x. Therefore, this thing is equivalent to sine squared x. Can you follow so far? Now, we're going to do a little bit of algebraic manipulation. I have gone from this, I've multiplied by the conjugate. I've used the Pythagorean identity in a unique way to get sine squared x. I haven't done much with this at all. I just have x times 1 plus cosine x. You follow so far? Now, because this is a limit, I can split up limits by multiplication, true? So I'll show you every step by step. Watch what we can do here. With our sine squared x, I know that I could make this limit of sine x times sine x. Is that not still sine squared x? Okay. Again, as x approaches 0. And then this thing, I'm not going to distribute that. I'm going to not distribute it for a very specific reason. Check this out. This is the same thing as x times 1 plus cosine x.
Okay.
So I haven't really changed that at all whatsoever. You're still okay with this? You sure? Raise your hand if you are. Feel all right with that? Good. Okay. Basic algebra. Here's the idea. Look at, because we can separate limits by multiplication. Check out what we can do. I can group together, because it's just fractions, this thing and this thing.
Yeah.
Do you see it?
Alright, let me rewrite this. Okay, so he's not distributing. Okay, split them up. Okay.
Does that thing look familiar? Yeah, so if we group it, then this is going to be the limit as
1?
x.
Oh, it's 1. Oh, okay. I'm gonna draw a line to that.
Approaches 0 of sine x.
Then you can plug in 0. Because cos of 0 is 1. 1 plus 1, it's 2. Sine of 0 is 0. It's 0. And what was the original? 1 minus cos x over x. Yeah, so it should be 0.
Over x times the limit as x approaches 0 of sine x over 1 plus cosine x. Very brief recap, very brief. We multiply by the conjugate. What that does is create a sine squared x for us. The sine squared x can be split up into sine x times sine x. The x times 1 plus cosine x, we don't change that at all. What we do is we group it in a certain way so that we can use a previously known identity that we have proven. That's okay, we're using something we've already proven. So now we have a limit of x, sine x over x, and a limit of sine x over 1 plus cosine x. It's okay to split up limits by multiplication. I taught you that property. Are you still okay with this proof so far? All right. Can you tell me how much is the limit as x approaches 0 of sine x over x?
1.
Beautiful. We just did that, right? We just did that. That's fantastic. So this is 1 times. Now, what I want you to do is I want you to try to evaluate this limit at 0. Are you going to have a problem with that?
No.
Are you going to have a problem? Why not? Why don't you have a problem now? What's sine of 0? Good. Is it okay to have 0 on the numerator?
Yeah.
Yep.
Sure. Does it make 0 on the denominator?
No.
Because you have 1 plus how much? 1 plus 1. That's 2. You have 0 over 2.
Yeah.
This is 0 over 2. Agree? So how much is 0 over 2? What's 1 times 0?
0.
Don't say 1. How much is 1 times 0?
0.
What that says to us is we've just proved something else. We now have this identity. That's identity. The first one we did, number 1. This is the second one.
1 minus cos x over x is 0. Yep.
The limit as x approaches 0 of 1 minus cosine x over x is 0. Interesting. You know, maybe you can remember it this way. Well, I do at least. I remember it this way. Something involving sine gives you 1, something involving cosine gives you 0. That's kind of interesting, right? Because usually it's, so if sine gives you 0, cosine gives you 1, right? If cosine gives you 1, sine gives you 0. It's almost the same idea here. The sine one is giving you 1. The cosine one is giving you 0. It's kind of cool, right? Same sort of relationship. That's how I remember it, at least. Would you like to do the tangent one?
Okay, I'm gonna do that tomorrow. Yeah, I've been going for an hour and a half. It's good enough.